So the first type of CPU organization that we'll learn of are called stack CPUs. These are very simple models, right? So along with stack CPUs, we'll also learn of a concept called as a zero address instruction format, right? So we'll also learn about zero address instruction format and how these instructions are executed, right, in a CPU. So we'll also understand about the execute cycle itself that we have not covered in depth in the previous video, because the execute cycle is dependent on the CPU organization or architecture itself, right? So let's understand the stack CPU. Remember, a CPU has broadly two components, the arithmetic logic unit and the control unit, right? So what does the arithmetic logic unit do? It performs all arithmetic and logical operations. The control unit does rest of all the non-arithmetic and non-logical operations. For example, it controls the program counter, because the control unit controls how the programs are executed in the whole system, right? Of course, the control unit also talks to the arithmetic logic unit, right? For example, the updating the program counter, right, in our fetch cycle, all of that stuff, fetching things from memory, all of that is controlled by the control unit. The arithmetic logic unit only performs arithmetic and logical operations, right? Control unit does rest of non-arithmetic and non-logical operations like controlling the execution of program, reading data from memory, all of that it takes care of it, right? So there are two broad components, your ALU and your control unit, arithmetic and logical unit. So your stack CPU, look at this whole white box, again, this is the logical schematic diagram. This whole white box is the CPU. It consists of your ALU and your control unit. In a stack CPU, what happens is all arithmetic and logical operations are done using a stack. Remember that this is my main memory, right? So this is my main memory. Within my main memory, I have a predefined space within my main memory where I'll store a stack. Again, stack is the data structure that we have studied extensively in data structures and algorithms, right? So it is that data structure stack, which is the last in first out data structure. So last in first out stack. Okay, that's the stack we're talking about. So a part of the main memory is allocated for the ALU stack. Okay, and this TOS basically stands for top of the stack. A stack has a top, right? TOS means top of the stack. Everything is pushed onto the top of the stack. Everything is popped from the top of the stack. Now ALU itself works with two registers primarily. One register is called the accumulator, right? One register is called the accumulator. The other register is often referred to as a temporary register. This TR stands for temporary register. I'll explain you how the ALU performs the arithmetic operations with a simple example. Okay, so let's take a simple program here. Again, this is the basic architecture. Now let's understand how the ALU itself works slowly. So imagine I have a bunch of registers, and let's assume this program, this instruction. First, this instruction is executed, wherein whatever is there in memory address 2080 in hexadecimal is copied to register A, right? So this, again, in your stack CPU, you can have instructions like this, right? So similarly, you will have an instruction like this, wherein we are copying from address 2090 to your register B. Similarly, from address 2096 to your register C. So I've copied the data that I want to operate on into registers A, B, C. That's what these three instructions do. They copy from your main memory. I'm sorry. They copy data from the main memory to your registers A, B, C. Next, from here starts the interesting part. From here, this is where the stack CPUs differ from other architectures. In the stack CPU, all the operations are performed using this stack. So first thing that I'll do is called push A. So because there is only one unique stack associated with the CPU or with the ALU, right? So push A basically means we will push this, whatever data is there in register A, we'll push it to the top of the stack. We'll simply push it. Initially my stack is empty. Right? So what do I push? I have only A in my stack. Then I say push B onto my stack. So B is also pushed, right? So look at this. This is a stack operation. Remember, push and pop are stack operations. In the case of, remember, in the case of your stack CPUs, they actually write data to your main memory because the stack itself is part of the main memory. Then here comes the most interesting instruction. There is an instruction called MUL, which means multiply. This instruction simply says multiply. This instruction is called a zero address instruction because there are no other memory components, whether they are registers or memory locations that it is referring to. It is just, so this has only a operand. Sorry, it only has an opcode and no memory locations, no addresses that it is referring to, whether they are addresses of registers or they are addresses of memory locations themselves. So here you just have a simple opcode like this. So the moment you execute MUL, what happens now? Now let's see, again, this is what is unique about your stack CPUs. So let's understand that step by step. Remember, before we go and understand the instruction cycle of the MUL operation. Okay, let's assume I have the MUL operation. Before we go and understand this, actually there is a small typo here. Let me just change this. Instead of add, it should have been mul. Okay, so I'll explain this step by step. Okay, first and foremost, we have understood about the zero address instruction format. This is called the zero address instruction. This is also called as a zero address instruction because there is only opcode here. There are no addresses either of registers or of memory locations that I'm referring to in this instruction. That's why these instructions are referred to as zero address instructions. Very simple, right? And zero address instructions are very, very popular as far as stack CPUs are concerned. In stack CPUs, what happens is your ALU instructions, all of your ALU instructions, all of your arithmetic logic unit instructions, all the instructions that are executed using your arithmetic logic unit are zero address instructions like addition, multiplication, if, all of them, right? Similarly, your non-ALU instructions need not be zero address instructions. Look at this. This is not a so this whole program is executing on a stack CPU, but this is not a zero address instruction. This is not a zero address instruction because here I'm both giving the location of the register and the memory location from where I want to obtain the data, right? So in a stack CPU, your arithmetic and logical instructions are zero address instructions. Your non-ALU instructions need not be zero address instructions. They may be, but they need not always be. That's very important, right? So now let's understand how this operation or how this instruction I6, which is mul, how is this executed? Let's understand the instruction cycle for this instruction MUL. What is this? This is instruction I6, right? So this is instruction I6. First, the fetch cycle. In the fetch cycle, what happens? We read mul from the memory to CPU, okay, based on the program counter and using the help of the control unit, right? Arithmetic logic unit and control unit, right? The control unit controls basically whether an instruction is executed, incrementing the program counter. All of that is controlled by the control unit. All non-arithmetic logical operations are done by control unit. So the control unit, based on the value stored in the PC, it copies this instruction mul from memory to CPU. That's what is the fetch cycle. In the execute cycle, what happens? First, this mul is, see, your mul is your opcode, right? Your mul is your opcode. The moment the stack CPU sees mul as your opcode, it says, okay, multiplication requires two operands, right? Multiplication typically requires two operands. So as soon as it sees this, it interprets the opcode, it goes to the stack and says, it starts executing these instructions internally without explicit. Look at this here. I'm not writing push pop anything, right? As soon as I have an instruction called mul, internally these operations are executed. So interpreting the opcode as mul, which requires two operands, and it has to perform the multiplication operation. That's what the CPU, the control unit, understands. As soon as that happens, now it will start popping. Now what will happen? Look at this. So let's assume my stack has A and B now, right? This is my stack, right? So this is my stack and this is my top of the stack, right? So first it fetches, so it says pop. So the first pop, let's see how the first pop works. As soon as we have the first pop, B is popped, right? B is popped and B is stored in the accumulator. Then as soon as B is stored in the, see, B is right now only stored in the accumulator. Let's not forget that, right? So now, okay, let me write this here. B is stored here. B is stored in the accumulator. Okay, let me erase this and write it properly. Okay, so B is stored in the accumulator. Okay, now again, the next operation is pop. Now in the execute cycle, the next operation is pop. Again, we are popping. When we are popping, now this is already popped, right? So my top of stack is here now. Now before I pop, I copy this whatever value is there in the accumulator into my temporary register. So B gets copied here. Whatever is the value of B gets copied here, right? So this is now I'm again performing pop, right? Which means this value now gets copied to the accumulator, and the accumulator gets overwritten. The accumulator gets overwritten. So what it had a value of B, now it will have the value of A. So now we got both the operands. Look at this. First we always pop the second operand. First we always pop the second operand as a convention. Next we pop the first operand. Right? Next we pop the first operand. So we got our B in our temporary register. We got our A in accumulator. Now these two, now what is the next operation that it has to perform? It has to perform the actual multiplication itself. This multiplication will happen in the ALU, and the ALU reads the data from the accumulator and the temporary register, and it performs A star B. This resultant value, it stores back in the accumulator. Okay, so in the accumulator now you have, see, look at this, it read these two values, A from here, B from here. It performed the multiplication operation as part of this chip, and it now stores A into B. Look at this, now it stores A into B in your accumulator. So now my accumulator consists of A multiplied by B. Okay, that's what my accumulator consists of. Next, the next operation it will run is push. Now what will happen is, now we have popped, look at this, now we have popped this, we have already popped this, which means my stack is empty. My A star B, whatever its value is, now is pushed onto the stack now. So my stack will contain A star B as my top of my stack. Look at this, these four operations, so these five operations actually. First is interpreting the opcode, one pop, second pop, popping the second operand, popping the first operand, performing the arithmetic operation, pushing the result. Okay, this is how exactly the execute cycle itself works, right? So all arithmetic logic operations are zero address operations, and all of them are performed using the stack itself. Okay, that's very, very important. Now let's see what we have. So we have A star B in top of the stack. Next instruction, let's continue with the next instruction. The next instruction says push C. So what happens? I have some data stored in register C, right? That value we want to push it to the stack. So I push it, my top of stack becomes this now. This is no more my top of the stack. Cool. Very good. Sorry. So let me draw the stack here. So this is my top of the stack. Then I have one more arithmetic operation called add. Now what happens with add? With add, what happens? First I pop C. Look at this. First I pop C and I copy it to accumulator, and then it goes to the temporary register, right? So C becomes my second operand. Let's write this down. C becomes my second operand. Then see, look at this. These steps happen, right? I interpret the opcode to be add, and I know that add requires two operands. First I pop the second operand, which is C. I store it in my temporary register. C is in my temporary register now. Then I have A star B. I also pop this, right? So my accumulator consists of A star B. Now an addition will happen between these two, and the resultant will again be stored in the top of the stack. So eventually my top of the stack will simply consist of A star B plus C at my top of the stack, right? So that's what will happen here. Now here, look at this instruction here. If you look at your mul and add, your multiply and add instructions, they implicitly perform the pops and pushes. But we can also explicitly perform the pop. Look at this line. Look at this instruction. This instruction says pop D. Now what is this instruction? This instruction says whatever is there in the top of the stack, pop it and store it in register D. So what happens now? My register D will contain A star B plus C. So whatever data is there in registers A, B and C, this mathematical operation or this arithmetic operation is performed. This resultant is now stored in my register D by the end of this whole thing. Now I can copy from D to any memory location of my choice if I want to. Very simple logic. This is how stack CPUs work. The most important thing about a stack CPU is all arithmetic and logical operations are performed using the accumulator and the temporary register by having all of your operands on the stack itself and using your operators or your opcodes to be zero address instructions. This is how this whole thing works. Very simple logic here. Now let's look at a simple problem here. Imagine I have a stack CPU, right? Imagine these are the instructions I have, I1, 2, 3, 4 up to I10. What is the resultant of this? Let's understand this. So let's assume B, C, X, Y, all of them are my register values. Okay, let's just for simplicity. So push B, which means in my stack I'm going to push the value of B. Then it says push X. So I'm going to push X to my stack. Then it says add. So when I do add, what happens? Look at this. This is my second operand. This is my first operand. So what do I perform? B plus X is now pushed to the stack. Right? So add basically finishes the operation, also pushes it back. So my stack now contains B plus X. Now it says pop C. So now what happens? C becomes this. My stack is empty. Okay, push C. Okay, now what am I doing? Pop C. So B plus X is now stored in C. C equals to B plus X. Push C. So what happens now? In my stack now I have C. And what is C? C is nothing but B plus X. Then it says push Y. So I push Y also onto my stack. It says add. So now if I add both of them, what happens now? What will I have? I'll have C plus Y in my stack. I'll only have C plus Y in my stack. Right? So this is what I have. Then it says push C. Again it says push C. So let's assume I push C now. Very good. Then it says subtract. So subtract. How does subtraction work? My first operation is the second operand. My second thing that I'm popping, the first thing that I'm popping is the second operand. The second thing that I'm popping, C plus Y, is the first operand. Remember the logic here. We always pop the second operand first and the first operand next. Right? So what happens here? So let's go back. Okay. So C I popped, C becomes the second operand. C becomes the second operand. Okay. C plus Y becomes the first operand. It becomes the first. It performs a subtraction operation. So at the end of subtraction operation, the subtraction operation is equal to Y. So Y gets pushed now into the stack. Right? So the effective value that I have here is Y. Then it says pop Z, which means my Z is equal to Y. So what happens at the end of this whole execution? My register C will have a value of B plus X. My register Z will have a value of Y. This is what will happen by the end of executing all of these instructions. Very simple code. If you know how to use a stack, how to push and pop into a stack, and again, very important thing is the first thing that you pop is a second operand. The second thing that you pop is a first operand. You just have to be careful about this order. Otherwise, we'll mess it up. Right? Very simple concept. Again, stack CPUs are not very popular in the real world at all because they are very, very time consuming. Look at this. Look at how many times I have to read from memory just to perform a simple arithmetic operation. But it is important to understand stack CPUs as a logical step towards more advanced CPU architectures or CPU organizations like your register based CPUs or like your accumulator based CPUs, etc. Right? So the next CPU organization that we'll learn of is called as accumulator based CPU, and they're actually real computers, early computers in the 1950s and 60s, which are actually accumulator CPUs. I'll discuss about the real actual accumulator CPUs that we will learn of in the next video itself.